iSCSI is a standard storage networking protocol that facilitates block-level access to storage devices by carrying SCSI commands over a TCP/IP network. It enables data transfers over LANs, WANs, and the Internet, allowing location-independent data storage and retrieval. Clients, known as initiators, can send SCSI commands to storage devices, targets, located on remote servers. Developed by IBM and Cisco in 1998, iSCSI presents a low-cost alternative to fiber channel, as it can utilize existing network infrastructure for long-distance connections, unlike fiber channel, which typically requires dedicated cabling. Hosts negotiate and exchange SCSI commands over IP networks using iSCSI, essentially emulating a high-performance local storage bus over a broad range of networks to create a SAN. While iSCSI imposes no dedicated cabling requirements and can run over existing IP infrastructure, its performance may degrade without operation on a dedicated network or subnet due to bandwidth competition. Organizations use iSCSI for storage consolidation, where storage resources are centralized without being tied to specific servers, making storage allocation more efficient. Additionally, iSCSI SANs are crucial for disaster recovery by mirroring storage resources from one data center to a remote backup location, allowing for swift migration of disk arrays across WANs. Initiators acting as iSCSI clients send SCSI commands over IP networks. They can be software-based, implemented through device drivers in the kernel, or hardware-based with dedicated hardware for improved performance. Initiators negotiate with targets to establish connections to logical unit numbers, LUNs, within iSCSI storage arrays, enabling access to disk volumes. Targets refer to storage resources on iSCSI servers and are commonly network-connected hard disk storage devices or general-purpose computers. Storage arrays within data centers often host iSCSI targets, including both commodity hardware with free software-based implementations and commercial products from various vendors. Common deployment scenarios include using iSCSI for network booting in diskless computers, with servers initially booting from local sources before accessing data storage over iSCSI. iSCSI addresses objects within the protocol using names like the iSCSI qualified name, IQN format, extended unique identifier, EUI format, and T11 Network Address Authority, NAA format. Initiators can locate storage resources using the Internet Storage Name Service, ISNS protocol, offering management capabilities similar to dedicated fiber channel SANs, although many iSCSI deployments do not require ISNS for operation. When iSCSI initiators and targets authenticate, they use Challenge Handshake Authentication Protocol, ECHAP, to prevent clear text passwords from being exposed. However, CHAP has vulnerabilities such as dictionary attacks and spoofing. Adhering to best practices when implementing CHAP within iSCSI can reduce these risks. Additionally, IPsec as an IP-based protocol can function at the network layer. The iSCSI negotiation protocol is adaptable to various authentication schemes, although interoperability challenges can hinder their widespread use. Administrators commonly establish logical network isolation by running iSCSI solely over segregated back-channel networks. This architectural setup limits exposure by only allowing management ports of storage arrays on the internal network, while iSCSI traffic operates on dedicated segments or VLANs. This approach addresses authentication concerns, preventing unauthorized users from communicating with storage arrays. Nonetheless, there is the possibility of a compromised host with an iSCSI disk, posing a threat to storage assets of other hosts, creating a transitive trust issue. Regarding physical network isolation, precautions must be taken to maintain the separation of ISI from the general network. Even though VLANs can logically isolate iSCSI, errors like incorrect cabling by technicians may compromise this security measure. Implementing color coding standards and labeling for iSCSI connections can help avert accidental bridging and ensure correct network connections. Some administrators opt for physically separate switches solely dedicated to iSCSI VLANs to prevent misconnection errors. Authorization in iSCSI environments necessitates strategies to prevent unauthorized access to storage resources. It's crucial to map initiators to specific target logical unit numbers, LUNs, to control access effectively. This approach ensures that initiators authenticate to specific storage assets they intend to use, maintaining a level of access control consistency throughout the deployment. Confidentiality and integrity in iSCSI transactions are essential, since the protocol operates without cryptographic protection for data in transit. Without encryption, attackers can intercept and manipulate data or compromise file systems, exposing servers to vulnerabilities. Employing IP-based security protocols like IPsec can provide cryptographic safeguards for iSCSI traffic, enhancing data protection during storage operations.